So today we're talking about game engine architecture. This is a little bit of the history of how we got to where we are, some of the ways we do things, and I'll also show off some of the discussion we can look at the end of the lecture on the architecture of Unreal. I also have an example of my son coming in and giving me some chocolate. That's alright, it's one of the challenges being at home. You have interruptions, but that's great. So what we're going to do is talk about game engines, and we can even go and have a look at some of the code from the id engine, so for Quake. So let's have I think everything is ready, so let's get underway. Free chocolate. Yeah, no, only free chocolate for me, not for everyone else. Unfortunately. So in-house coding. So what were game engines? Game engines initially started, everybody built their own game from scratch. So if some of you did processing in Segra 151 or have had to try and create your own games from scratch, there was no engine. It was just you program up how to draw things on screen, how to read an image in from file, how to move it from scene to scene. You did everything from the ground up. And what happened is once you've written one game, you then wrote another game. And that second game you wrote, you started reusing bits from the first game that you wrote. And so this idea of starting to reuse code and seeing, all of my games have to load images. Maybe I should create a loading image function and a file that's image loading. And there's a math library. I'll use one of them as well. So I'll grab a math library. And so this idea of reusing components of your previous code started then moving to, can we share those components with people outside of our projects? And so what game engines do is they are that collection of reusable code that people found when they were making their own games. And there have been a couple of game engines that were built with the intent of them being game engines, but most are people building something because they were building a game. So Unreal, for example, actually is built on top of SDL, and they were using the Standard Dynamics library, so they were using low-level open source code and building up to make games, and then have turned that into something reusable. So they're glorified libraries. Yeah, to some extent, kind of glorified. Well, they're actually glorified config files, technically. So the very first ones were just how you write a config file so that you can configure how things go. And then you started adding, so the scripting parts added to that, and they moved more and more out of what they considered core into the things that you could customize about this particular version of your game. And then, you started packaging that as, okay, I can build something that runs all this underlying stuff, and then people just throw in different images and they throw in different, some logic commands get changed. But, so you'd have in game engines, you'd have things like you could have a C in raw C++, you would have these window handles, right? So there's an HWND as a handle to a window. And you could get a pointer position, and then you could take the window handle and that pointer position and get a relative position in your game window of the mouse that was on screen, right? Because of course your window isn't necessarily the whole screen. So for doing that, you wouldn't want to have to rewrite that every time you made a game. You would want that built in to some sort of simple library or something that you would just use, right? So that's kind of how something like Unity, which was, the mouse position gets input.mouse position. In Unreal, you can just ask for mouse position. So if I go to Unreal Engine and I go into a blueprint, I can just mouse position, get mouse position. There we are. There is getting mouse position. So that's the Unreal way of getting mouse position, and that's got a location X, location Y, and a return value. So that's the X Y is on screen. So if we go back, tink. So these are different ways of getting the mouse, but for each of these player inputs, usually we use a keyboard. Once I've made a game with a keyboard and mouse, I'll just reuse that kind of controller. Potentially I build a configurable controller, whack that into the engine. I have AI systems in most games. There is a state of the world that you're playing in. There are physics associated with the state of that world. There are standard outputs like graphics and audio and haptics. These are all kind of standard ways of interacting with game worlds, and so they've been built into the engines over time. So this all started, as I was saying, as config files. So as config files, you have like .ini, .config, even JSON formats are now used for setting values. And so if you're writing a program and you have some things that you want to be available to the player or the person making versions of your games, you can put them into a simple config system. Now, if you've done Comp 261 either this year or last year, you had text processing. You did some parsing of text. Understanding that, you know how you could turn a standard text-based config file into something that could use slightly more complex configurations. So if you had n equals 5, you could then use n times 10 in a config file by using some simple mathematics, right? Simple coding, tokenizing of strings and processing of those strings. And this is what happened. We started having these config files become more and more complex. And so if you look at JSON, you could have a whole bunch of configurations which would set up what would happen on clicks, right? And so this allows you to change some of the features in a modified version of your game. This then built into, and that's got a bit wide, built into something like Lua, which is a full scripting language. Okay, so Lua was used for World of Warcraft. You could configure your UI by using Lua, because Lua was the HUD control language, and it's an interpreted language, and it can communicate between the core library, and there's a Lua basically stack parsing system where it passes values over to a Lua interpreter. The Lua interpreter processes those, and the Lua can call parts of your program that you explicitly expose to the scripting language. And so this was built basically on top of this idea of configuring things until the power in the configuration language became so much that it's its own programming language and you can do your own things in it. And there are a bunch of games that still use Lua for configuration because it's a relatively simple programming language. As you can see here, a for loop for I equals -2, 2, do array I equals I times 2. Now, this would break in a whole bunch of different programming languages, but in Lua, it wraps this range into a range that will work in the array. It does the lookup, so it's quite a different language, but it is a scripting language that came from this idea of turning config files into full scripting languages. Now, if you're making your own game, right, and then deciding, hey, well, maybe we should allow our artists to mod the game or allow people to mod our game. Adding in these kind of scripting tools allows you to keep your core language and, say, memory allocation, so you don't worry too much about seg faults. You do that all the core features of your game are held privately, and you only expose some functions. And that's to some extent what both Unity and Unreal do, is that they have a whole bunch of code that is the core game, and they expose some features. In Unity, you don't get to see any of that underlying code. That's all theirs, and they only expose some functions of the core game to you so that you can interact with LuaScript, C# into their exposed functions from the game engine. For Unreal, they also give you the full code of the game engine itself, and you can build the entirety of the game engine from source. You need about 90 gig worth of space because you need to build all the intermediate files for every C file in the entire game engine. So it's a bit of a big build, and then it compresses down once you finish building it. But that idea of taking games and modding them, when you make games possible, you get games like DayZ, which is that modding of the Armour franchise by a New Zealander, Dean Hall, who actually did some of my... he was a first year when I was lecturing at Otago many years ago, but he went off to Europe and ended up making DayZ and forming his own game company. And initially, what the mods were basically just changing some of the art assets. You'd go in and you'd find where the art assets are stored, and you'd just replace them with your own art assets. But you could also go in and get a hex editor and change the internals of game executables, because you can look at a game executable as a binary file and then go in and change some of those bits. Now, some people did this to remove DRM restrictions. So some of the DRM restrictions were there was a function call that ran off and did an external check with the server and would come back and give you a true or false depending on whether you were verified. What some people did is they changed the actual binary code to change it to always return true for some games, and were able to hack the DRM restrictions that way. You can go in and hack the particular images while they're in the thing in there, or sometimes they're able to change paths. Changing logic was harder on just simply hacking the executable, and that's where games started opening up these APIs. So I've seen that. Sorry, my Zoom. So sorry, people on Zoom. I had not realised that I hadn't been sharing on Zoom, and I only just saw that now. Oh well, it's being recorded, so that will be up. Sorry for those people who missed out on the Zoom. I've only just got to it, so yes, Lua was made in Brazil, which is pretty cool. And I've got to go back to the slides. Right. At least we've got more than one way of accessing this information. So as modding grows up, it goes from just modding games to actually saying, well, as we start building version 2 of the game and version 3 of the game, we start seeing that there's a core functionality which is being reused multiple times. And in fact, a colleague of mine said that they use the rule of 3. If you reuse a piece of code 3 times, you have to rewrite it. Because the first time you write it, it can be as hacky as you like, because it's just getting a job done. If you reuse that code, then that's kind of an indicator that maybe actually the function you were trying to implement is more core to what you do than just something I'm knocking up quickly. Once you're trying to use it for the 3rd time, you go back and you look at it and say, right, okay, this is obviously something I'm going to keep using. I need to make this clean and reusable and well-written code. That's when you put the effort in to make it good. So that idea of doing that meant that you had code that was well written, that is now available for other people to use, right? So fundamental similarities, we looked at player input, player position, graphics, audio, networking, finding all those similarities in games. We also have this idea of game programming patterns. Now, if some of you have done any of the software engineering style courses, there is this idea of a pattern being a standard way of doing things, right? So rather than a pattern, so rather than just reinventing the wheel every time, what we do is, well, okay, there's a pattern for doing this. How do we follow that pattern? The game programming and game engines actually move you in that direction. It was interesting that the Unreal people, when they were presenting at the GDC last year, were talking quite strongly about reusing the character component system and looking at how the systems are programmed well in Unreal and learning from those patterns how you should make your own files. Right? So this idea of, as I showed earlier today, when you're in a blueprint, one of the things we did here was, not that blueprint, and this blueprint, I took this function here, which was this ground distance, and it actually, I collapsed these nodes down and said, I'll just collapse those to a single node so that, not the construction chip, so that, event graph, so that they are easier to understand, right? So it's just doing that job there, right? So this is the ground distance, and instead of being multiple nodes here doing something complex, I now bring it down to a single node, and we have a comment area around it. These are those practices that make your programming more understandable and easier for other people to follow. And so these game programming practices aren't just about finding the standard way of doing things. They're also a way of helping other people understand what you did by communicating in a known format, right? So event processing is very common in games. In Unreal, you see that when we come in here, and it does, I've got to grab the right thing, the event tick, right? This is what's coming out of an SDL event handler, which is saying every cycle that the physics engine does an update, issue into a stack, or I put into a list of functions all the objects, and then go through those objects and call event tick. So once per physics update, I will go through my list of entire objects and call event tick on each one of those objects, right? So you could write this yourself. It would just be a loop through all objects calling event tick. Now, it also, if we have a look here, we can have a look at some of the other, it has event begin play. It's very hard to see that because it's grayed out. So event begin play and event actor begin overlap. The actor begin overlap is when somebody hits you, you need to respond, right? So this has been put into a list of overlaps, right? So at the moment it doesn't do anything. It just the physics engine just handles its physics. But if you have this active begin overlap event triggered, it means when the physics system finds a collision, it's going to call your special function to do something interesting, as well as if you've got physics turned on, it will apply physics to it. So these were events that were raised and that you can then handle. In the constructor script, you get a single event construction script. That event is called when you're constructed. Right? So bang, it sends an event. It opens up on that in that state. So event handling, very simple in terms of code, right? You just have an array of all objects, do a for loop through the object going object dot event tick, and it calls the function. Often you'll send it the delta time. When you start doing event processing, one of the things that you might have done if you were doing some naive game programming, and you might see this, we see this in the first year, Sigma 151, when people do processing stuff. When I hit a key, the naive thing is to say, right, update. So if I press A key, update my X position to be -1. Right? So, or -1, I suppose that way. So if I update my X position to, well, it's actually, yes, I am that way. If I update my X position by -1, I will move my sprite across the screen. The problem with that is if you do a direct mapping between a keyboard input and a screen position, how do you do physics? How do I do collisions? Do I move it and then work out the collision? And once I'm overlapping, what do I do then? Because then I just explode. It's kind of, oh, no, I need to know the position it's moving from, the position it's moving to, the speed at which it's moving. Like, I need lots of information to do any of the physics things I might want to do in a game. So I decouple this idea of me pressing key changes position on screen. What happens in the game engine is you make a request. Your event is pushed into the event queue of all the things that happened since last time I did a physics update. With that, I then go, the physics engine looks at all the requests. So when you press A, that's you requesting, can I move left, of the physics engine. The physics engine then does all of its calculations and either moves you left or not, depending on how the physics works out, or if there is collisions, or if you've got the ability to move, or any other restriction that might be on that event request. So now, instead of direct manipulation, we are only asking the game engine to do something. And in fact, you never, and for some game engines, they won't let you directly change the position of an object. Some game engines will let you do that, but they warn you that if you set the position of things, you could have the physics explode, right? Because the physics, if you set position, the physics, you've teleported into that location, the physics might not know what to do at that point. So it's better to use forces and accelerations than setting physics directly. Yes, physics isn't, well, not just hard, it's also mean. So also we deal with multiple events processed in a single frame. Now, this allows us to decouple frame timing from physics timing. So what you might well know that 30 frames a second is how 24 in movies, 30 on slow monitors, 60 on okay monitors, 90 on good monitors, 120 on really good monitors. Now, you wouldn't want a game running on a 30 frame per second monitor to be 1/4 of the speed running on a 120 frame frame monitor, right? So you wouldn't want the game to speed up. I actually used to play a game called Sock with Camel many years ago, and it was locked by frame rate, and so if your computer was faster, your game became unplayable. And back in the day, this is before almost any of you were born, there used to be a turbo button on big stand-up machines that would actually slow down the CPU cycles so your games could run more normally, because they had made computers so much faster and they weren't using delta time, they were just being frame locked, and so the faster your computer could run, the faster the game would be. Now, this idea of separating out physics updates from screen updates and always using delta time. So all of the game engines will have some concept of delta time so that you can manage the speed at which your physics is updating independently of how many frames are being updated. And that tick is a physics tick, and it has a delta time associated with it, so you know how long it's been since you last updated. And that will depend, a whole bunch of your physics and movement depend on time, not on number of times the player has theoretically seen the image. One of the other things we do in game engines is we've separated out the concept of a camera from the world. So the camera was this idea that instead of changing the position of an object on screen, I will change the position of an object in the world and then I have a camera, and the camera knows its relationship to the world and its relationship to the screen, and so the camera takes the world view and projects it onto the screen. So there's this camera mapping thing that is separate to moving an item on screen. So I no longer think of moving objects on screen, I think of moving objects in the world, and then my camera translates from world onto screen coordinates. Okay, so that's also a common architecture in games, is that you have cameras and you manage cameras. Even in 2D games, which are top-down and ISO, and it feels like this should be, top-down orthographic. And it feels like, yes, position there in the world is top corner in the screen. But even then, it's good to have a camera because you get to use the pipeline of the game engine because that's how it's been set up. Yes, world space, screen space, camera space. All things you need to know. World, window, and screen. Window or camera. And you need a bunch of functions to control the actors and the cameras. And we have a whole bunch of standard asset pipelines where we load content and we load displays. And if we look at game programming patterns, you can go and have a look at a whole lot of patterns for game designers, right? Game programmers. This is it's a bit large. But it goes through and gives you examples of and it's a free ebook that you can look at what are good game programming patterns, right? So ways to solve problems that you've thought about, but you're thinking, well, what's a good way of solving this problem? This is a good location for those information. Okay, so some examples. Oh, and now I'm going to get some overlaps that are a bit unfortunate because I've changed my ratios. So MIT developed Scratch, and this wasn't developed as a we need to make a game. This was developed as a we want to teach people how to program, right? And so they built Scratch in an event-based functional way. And so in Scratch you have these blocks of code which you plug together, and again there are events that come in, and from that event you have a block of code that follows it, and another event you have a different block of code that follows it, and you have timing events, and so you have all of the game engine components in terms of handling display and handling mouse inputs and having a way of implementing logic. So all of that's in there. It's just in a relatively simplified way. It also limits the kind of games you can make, but it's an excellent first programming language, and it's a game engine. Not that you'd make AAA games in it, but it allows you to start thinking about what an engine is. You then start moving to things like JavaScript libraries, which are not quite full game engines, but start getting close. So I've used Pixie.js for a bunch of mine, which is kind of an animation library. If you want to go full game engine on it, and I didn't include this, is you would go to Phaser game engine. So Phaser is a game engine built on top of Pixie.js and is an HTML style game engine designed for building web-based games that are mostly 2D, right? So it has fake 3D, but it's designed around being 2D. And if you go to Pixie.js, so if you've got if you actually spell things correctly, so if you've got a younger brother or sister who has, or younger sibling, who has been using Scratch, Pixie might be something that you could start introducing some of the text-based components of games. So you can see here, these are various examples, and I can change some of the numbers in here, so I can start seeing, okay, I'm looking at that saying, okay, they're rotating at that speed. I've got a for loop running, which creates them all, and then app ticker add. So this is the app ticker, which is that remember I talked about a tick, a world tick, and we have that in Unreal. This is the same ticker with a delta, and this is saying, you know, container rotate 0.1. Let's make that 10 times faster. So I can go in there and go 10 times faster, and reload, and now they're going 10 times faster on that rotation. Okay, so this is kind of start saying, well, you know, this is the text for it. There are certain things like the app ticker, which is built in, so you don't have to try and write those bits yourself. And this ticker.add is saying take the normal ticker and then add an additional this as an additional block of code to the code that is run when you've done the ticker, because the ticker will update a whole bunch of stuff, and then you're adding this new thing, and it gets past a delta, so it knows how long it's been, and that's where it uses it. Oh, sorry, is my audio gone weird? I hope that's not everybody. Let's go back to there. So Pixie, we then look at things like Game Maker Studio, which is again a 2D drag and drop with scripting. A game engine a game that they have made intentionally for helping people make games, and has actually been used to make commercially released games as well, though is somewhat limited still. Right? But is a good transition from just scripting into actual game development. Discord bitrate failure. So okay, I'll see if I can change my. I thought I had. Oh, I hadn't boosted the server. I'll have to boost the server to make my Discord better. I just have to get my boosts out of the other server. So the next game engine I was going to talk about is is Ogre 3D. Or you could use a different one called Panda 3D. These were both open source and free. Now, Ogre was a game engine that was a commercial product. They were trying to compete with Unity and Unreal. And then I think about 7 or 8 years ago, when Unity and Unreal both went free, Ogre did the, hands up, we can't compete against free, because we were trying to be the low-cost version. But when they both went free, it was, well, we can't do that, so we're gonna have to go open source. They released all their source. They basically closed the commercial aspect of the company and made it an open source project. Panda 3D is I believe UCS, University of Southern California, USC rather. USC made a game engine for its students, and so they've released that as open source. Both are quite good game engines. Both have reasonable 3D support and technology, and are being actively developed. So if you're wanting to go a 3D game engine that's open sourced and kind of Panda has more educational aspects, that's a good option. For next year's game engine programming course that I'll be teaching this trimester, trimester 2 next year, we will be using Godot and Unreal. Godot is again an open source game engine that has been doing a lot of really good active development in the last couple of years. So if you, and to some extent also the hardware requirements. So some of you might have noticed that Unreal 5 uses quite a lot of your hard disk, right? And some of you have been having to delete games that you play, even the games that you're currently playing, just so you have enough disk space to run Unreal and build games. For Godot, the current size is much smaller, right? So the footprint of the game engine and the footprint of the games you make are much smaller. Again, you're not encouraged to get the massive mega scan, terabyte sized textures, but hundreds of gigabyte sized textures, but so getting this game engine It is very actively developed. It's actually improved quite a lot. So 3.4 is actually getting pretty good, and they'll probably be doing Go.4 by the time I actually teach the course. So these have a lot of features that are like game engines, the big game engines, and they build actually quite good both 3D and 2D games. Right, so we're going to also include this because it allows people on much lighter weight hardware to still be able to learn about game development. Right, so yeah, so we can't really kind of restrict people to say only if you've got massive hardware. So if you wanted to develop in a more programming, this doesn't have the node-based programming approach. So the blueprints, so it is a bit harder for artists to just work with you because they don't have that layout scripting collaborative tool that blueprints are quite nice for. But as a programming environment for programmers, it's quite a good engine. And if people were struggling, and if we decide that Unreal is too unwieldy for some groups, then we may be able to roll back down into Godot for those groups so they could make their final product. This is for the programming only, so 313 only, that we can negotiate if you want to use Godot as your game engine. I've supervised other Godot projects recently, and they require a wee bit of understanding the dynamics of Godot, but that's also possible to do. So although Godot isn't used by companies in New Zealand, so it's not something that you can necessarily would be using if you went out in the industry. You would still understand the basics of what a game engine is. And of course, we have the big two, Unity 3D and Unreal. So again, they look relatively similar with details and sidebars and content, and all of these are relatively similar between them. And so the major differences, I would say Unity is got a far better 2D system and a far better mobile development pathway. Right? So if you're interested in developing for mobile, Unity is just better than Unreal at this stage, and probably will be for a while. Unreal has better high-end graphics and better lighting and details and textures, and so and the film industry use it, so it's got a higher end capacity. How about MMF 2.5? I would have to find out what MMF 2.5 is. I haven't been following that. So yeah, so these two are ones, and you've got films like The Mandalorian, TV series like The Mandalorian. All right, so MMF 2.5 is so this is a YouTube video. I won't play you the whole thing because it's 17 minutes long, but it's a discussion of using Unreal to create The Mandalorian, and the scenes were actually created in yes, it keeps wanting me to jump out and click into the right place. I'll just stop him talking. Oh, and I need to stop him talking here. Bang. So they had this area here, if it actually plays. This is our screens. So you're actually using Unreal to project onto the screens, physically LCD screens, the scene that the actors are acting within. And so you have set, and then this white area is actually screens that they can project images onto. So you're acting in front of, like a green screen, right? So instead of a green screen, this is acting in front of actual monitors that are displaying the world the game can see. And then when you composite it, it uses the real footage, so it gets rid of those screens and replaces it with actual high quality 4K resolution game content generated for that scene. but it means that all the reflections are right. The actors know where to look because they know what's around them. So all of those aspects of the world are correct, right? And so that is very useful when you've got a lot of shiny objects like they do in The Mandalorian. Now, we're looking at also using Lumen Nanite in Unreal. This is the new, and so a couple of these are now standard in Unreal 5. Yeah, so the scenes are great, but the limited space means that the chase scenes, etc., are very limited. Yes, you notice some of the constraints and the way that they do chase scenes, and some of that flow isn't there. They kind of use cutscenes to try and make like having things going past, and you cut to having other things going past, and so you don't have those flowing cutscenes where you pull out and see something moving. So yeah, so there's you've got different visuals that you can do when you've got those sets set up that way. So global illumination in Lumen and Nanite for geometry. Those are lectures in themselves. And in fact, you now also have ray tracing on RTX 30 Plus series hardware. Is that they've got ray tracing built in to the game for real time ray tracing, right? So you can use real time ray tracing to do some of the shadows and some of the illumination aspects of Lumen's real time illumination are using the ray tracing features of the 3000 series RTX machines. Now, you can learn to program that all up from scratch, but that's a lot of work, right? There's a huge amount of work that goes into getting all of that working, and you probably don't have the time to worry about that. Now, if you go into the documentation, you'll find various diagrams of the game state, and you have player controllers and AI controllers controlling pawns, so you can go and, because Unreal Engine is open source, you can dig in and download the full source. Again, that's a lot of files, and look inside the architecture. You will find SDL2 calls, which is what I found when I was looking at some of the event handling, and you can see exactly how they set up all of these callers and controllers. For this one, this is just saying that you have a player controller and AI controllers they possess a pawn. So if you have a pawn in your game, your player can control that. So an object moving around, that is your interactive component in the world. A player can control it, right? So I've got my player controller, or an AI can issue it instructions, right? So that's what it's saying here, is that there is something that possesses a pawn and overlaps. In here, the player controller has a HUD, inputs, and the player camera manager. So that's all under player controller, and AI doesn't have a HUD because the AI doesn't need to know additional information. And yes, Unreal has a massively deep and complex class hierarchy. I didn't know if I really wanted to go into the full let's dig down everyone. If you want me to, we can in later lectures. One of the ones I thought I would show, and in fact I know I've only got a minute left, so I will see if I can find where I had it. And it was... Oh, did I put it up here? Nope, just a sec. I have to find where I put my other window. Ah, there it is. So I've also shown this in Prezi in various times, and it's Prezi Classic I need to go to. Where are they? Ah, a couple of years old. But the bit that I wanted to show you out of this lecture slide deck, which I created a few years ago, was actually which is again for this course, is if I go down, this was me kind of describing a game engine as loops and updates. But one of the things I thought was quite fun was having a look at the id Tech, so id Tech 4, so for Doom, so this is the original Doom, you had the game engine, right? So the game x86.dlls, which had actors and cameras and entities. And then Doom had its specialized features that played on top of that DLL. The game engine was just a library, right? And it had other libraries for maths and standard parsing and geometry and hashing and standard lib TLLs. But if we actually look at the C++ code for Doom, it had things like sys set physical working memory. Now, 192 double arrowed 20 and 1024 double arrowed 20. So what that means is, if you can guess, is this was between 200 meg and 1 gig of memory that was being physically allocated. Right? So how much RAM was this going to want to take? Right? So if you had less than 200 meg of RAM, you couldn't run Doom, right? And it would ask for up to a gig of your RAM to allocate to the game so that it would run. Okay? And then you had the critical section things, but then look here. We've got some what I would consider incredibly ugly code. While 1, so forever, sleep 16666. That is so it runs at 60 hertz. It's doing a micro sleep. So this is a async start thread. This is saying once every 60th of a second, you will come through this. You will sleep for the 60th of a second, and then you'll call common async. Right, so that's actually where it will do the job. And sys trigger event 1. So it's saying run the async, say that I've triggered, and then check if it's been cancelled on the main thread. Right, so test if the game has exited, and so I need to exit this thread. And then later, after it, so it's set up that async processing, and then here in common frame, it has session frame, and then just does a for loop through game ticks to run. So how many ticks I should call. So if there've been 10 physics ticks since my last view update, it'll go through this cycle 10 times, and it goes game tick, frame run, for entities equal active entities next, entities not null, get the next active node, right? So it goes with the active node, finds the next one, and then just does physics, get physics, update time. So it says to the entity, hey entity, grab the physics associated with you and tell that physics to run one update step. So in Unreal Engine, that would be the line that would call that tick in your program, the event tick that you then build a blueprint over, is the function that gets called from here. Right? So this is, and that's the event logic. Right? That's the physics update logic in this in Doom. No magic, just relatively straightforward CPU calls. Right? Update screen's false. So so what it does here is it tells it to not update the screen, and then draws to the screen, and then resets the end frame, and issue render commands. So what happens is it says, hey, once I'm about to draw to screen, stop the screen displaying, draw to the back buffer of the screen, and then reinitialize the screen displaying again. Right? So it kind of, if the game pauses, the screen still has something on it, and it will draw to the back, but that copying to the screen needs to be paused while it updates the back, so you don't get screen tearing where you get some of the update on screen from the new frame and some from the old frame. And so that was the bit where it locks the screen to prevent tearing between frame updates. Right? So again, it looks like this stuff is really big and complex, but actually relatively straightforward C++ code that is actually running the actual game engine in this case. Okay, so that was now we can also go and have a look more in the blueprint, and we can start talking about what the full architecture of this game engine looks like. What you need to understand is basically, I suppose, where your bits fit. And once you, we're not going to advise you to build the Unreal Engine from scratch and start changing the actual game engine code itself and then recompiling that. That's a mission. And also should be unnecessary for any of the games you can think of making in a small team by the end of October, right? So we don't expect you to dig into the game engine. But understanding where these things come from and how they interact is very useful. And so that's what we that's where we need you to get to is kind of starting to understand how to use the tool and where these features come from and how they relate to other game engines which you would then have to use in the future. Okay, so if I... Okay, it ended my Zoom call because I was the only person in the Zoom. So sorry to the people who tried to be in person in Zoom. In 118, I forgot to turn the Zoom on. But hopefully that was an interesting introduction to the game engine architecture. One of the things that you will have to wrestle with is figuring out the right way, the easiest way of doing things in the game engine, and the way that the game engine intends you to do things. And so, although you can do things in many different ways, looking at the way other people do things and working together is generally the best way of doing this. Okay, so if we grab... Wow, my machine has started going really slow. Okay, so yes, many things. I've got too many things open, and as you see, if I show you my list of yes Chrome windows that are open, I've got far too many open. Okay, so that's the end of the lecture. It's just gone 5 o'clock. Please go in and vote. And yes, I've got all of those running, and I have Unreal running in the background here, and OBS, and what are these? Yes, a bunch of other things. I've even got my Inkscape running for doing diagrams and things. So yes, unfortunately my laptop is running too many things, but you know, it's a modern laptop, so it's not too bad. Look at that taskbar. Yeah, no, the taskbar is horrendous, and my memory is overused. I have to clean up quite regularly. So thank you all for coming along and paying attention. If you have questions, dump them in the Discord, and I will be online on Monday. I would like you to start voting on topics. I saw in this area here, if you can vote on those topics in... Oh, not that one. But... Not that one. That one. So if you could vote on these topics, then that would help me with the order in which you want to do things. I think the next lecture I might give is on balancing these game engines up. Today's talk I went through adding a C++ objects. I took a while to explain how that worked, and I also got myself lost in a bit of code there. So I will do a cleanup video that's a very short example of the way to do it and have that working, where you can add a blueprint function. But if you have specific requests please ask me, either by voting in this repo, by creating a new issue in here if you can. I think you can. I'll check if you can, and if you can't, tell me, and I'll try and set it up so all of you can make new issues. And so what I want you to do is tell me what it is that you need me to tell you about the course and what you need to learn. Okay, so hopefully you've all started playing with Unreal at least a little bit, and we'll talk to you on Monday, if not on Discord before then. Okay. Have a great evening. Thank you very much, and yeah, we'll see you next week. Stop recording.